Okay, so we've seen previously that the available results on the existence and uniqueness of large area constrained Wilmot spheres in manifolds that are asymptotic to Schwarzschild are somewhat unsatisfying. And this is really what Michael and I tried to remedy in our recent work. And in order to present our main results, we need a few more definitions. So we're going to consider a manifold that is asymptotic to Schwarzschild and a sphere sigma that avoids the complex set K. And then we're going to define the area radius lambda of the sphere to be the radius of a Euclidean sphere that has the same Euclidean area as sigma. So this is the first equation over here. And then we're also going to define the inner radius of such a surface sigma to be the distance to the origin. And as you will see shortly, the ratio of these two quantities somehow measure how centered such a surface is in the asymptotically flat chart. And then moreover, we're going to call a surface sigma on center if it encloses the origin in the asymptotically flat chart. And if it does not, we're going to call it outlying. Alright, so to explain these definitions, there's a few illustrations over here. So on the top left, we have an on-center surface where area radius is about the same as the inner radius. And on the top right, the surface has been moved to the right, so it's now less centered, and in particular the distance to the origin has increased. So in this example over here, area radius is larger than the inner radius. Then on the bottom left, the surface has been shrunk and moved to the right, so that the distance to the origin is about the same as over here, but the area is now a lot smaller. So in particular, the inner radius is now larger than the area radius. And moreover, the surface doesn't enclose the origin anymore, so it's now outlying. And then finally on the bottom right, we have a surface that is on center, which you can probably barely see because the distance to the origin is very, very small compared to the area. And in particular, in this example over here, area radius and inner radius are on completely different scales. And it turns out that these kinds of surfaces are by far the most difficult to study, and I will explain to you shortly why. Okay, in any case, let me now present our main results. So together with Michael, we proved the following. So we consider a manifold as asymptotic to Schwarzschild without any smallness assumption. The only thing that we assume is that the scalar curvature is non-negative. And then we can prove the existence of an asymptotic family by area constrained Wilmot spheres. So more precisely, what we show is that for every sufficiently small positive number kappa, we can find a large on-center area constrained Wilmot sphere sigma kappa whose Lagrangian parameter equals kappa. And then as kappa tends to 0, the inner radius of these spheres tends to infinity, so these spheres move off to infinity. And also the ratio of area radius versus inner radius remains bounded, so these spheres don't become completely off-centered. And in particular, what this means is that this family over here sweeps out the complement of a compact subset. Okay, then additionally, if you assume the same growth condition as for stable constant mean curvature spheres, so again, if you require that the modulus of x squared times the scalar curvature is radial and non-increasing, then you can prove the following. So if you have a small number delta, then you can find a large number a such that the following holds. If you have a area constrained Wilmot sphere sigma that's outside of a large complex set K, so this is the first additional assumption. And if you require that the tracer second fundamental form of the surface is small in L2 sense, so this is the assumption replacing stability. If you require that the area of the surface is large, and then if you require the following centering assumption that lambda divided by rho is less than 1 over delta, then the surface has to belong to the family constructed up here. Okay, I really want to emphasize that this is a considerable strengthening to the previous results because first of all, we are able to consider all manifolds that are asymptotic to Schwarzschild, so there's no smallness assumption whatsoever. The only thing that we require are conditions on the scalar curvature. And also the uniqueness result is a lot stronger because the only thing required over here is some sort of comparability between area radius and inner radius, whereas in my previous result, I required that lambda is about the same as rho, whereas over here you can choose delta as small as you like. Okay, there's a few remarks that I would like to make. So we have these assumptions on the scalar curvature for existence and uniqueness, and it turns out that they cannot be relaxed. So if you drop the assumption that the scalar curvature be non-negative, existence might fail. If you drop the growth condition, uniqueness may fail. The second remark is regarding this small energy assumption. which might seem a bit technical to you. However, you can show that if you have a surface with non-negative Hawking mass, then it automatically satisfies the small energy assumption. And of course, non-negative Hawking mass is a physically very appealing assumption. The third remark is regarding the question if this asymptotic family actually forms a foliation of the complement of a compact subset, and at least if the scalar curvature is asymptotically even in the sense that the odd part decays like small o of mod x to the minus 4, we can prove that this is the case. However, in general, this seems a pretty difficult question, and I think in particular under the assumptions of the previous theorem, this is not always true. So this is a interesting problem that would need to be studied sometime in the future. Okay, then the fourth remark is regarding the asymptotic positioning of these surfaces, and we've investigated this in a lot of detail in a recent paper, and what we were able to show is that if the scalar curvature vanishes outside a compact set, then the barycenter of these spheres asymptote to the center of mass of the manifold, so we get the same result as for large stable constant mean curvature spheres. However, if the scalar curvature doesn't vanish at infinity, then the asymptotic positioning of these surfaces isn't determined by the center of mass at all, but rather by the asymptotic distribution of scalar curvature. So in that sense, area-constrained Wilmot spheres are able to detect some features of the initial data set that large stable constant mean curvature spheres cannot see. And then the final remark is regarding the centering assumption, because although this is an improvement to previous results, it would of course be nice to remove this assumption altogether. But as we will see shortly, this is pretty difficult, but we still hope that in some forthcoming work we can remove this assumption. Okay, so here's an illustration of the previous theorem. So the cross marks the origin in the asymptotically flat chart, and the dotted lines correspond to the asymptotic family by area-constrained Wilmot spheres, which in this example over here actually forms a foliation, so there's no self-intersections. And now the question of uniqueness boils down to asking if there can be other large area-constrained Wilmot spheres. And one candidate on the left is on center, and area radius is larger than the inner radius, but these two quantities are comparable, so we can rule out that such an area-constrained Wilmot sphere exists. Then in the middle we have an outlying surface where inner radius is larger than the area radius, so we can also rule out that such a surface exists. But then in the example on the right, we have an area-constrained Wilmot surface where area radius is a lot larger than the inner radius, and so far we cannot rule out this scenario yet.